Right. Our next topic is state space model, state transition, and related topics. Uh, these are the references. You can refer to chapter 5 of uh, course book, Digital Control Systems, or chapter 3 and 4 of Tewari's book, Modern Control Design. Maybe either both of these books, or at least one of them, is online available. If you search it, right, you can find a copy. Just look at these chapters and for more information, right? Okay, so let me first put this into perspective. So we spend a lot of time on writing dynamic equations of a plant, differential equations, and then get to transfer functions and so on, right? So that is a quite a wide breadth we have already covered. Now, every time we takes a control system, a plant rather, either we stop at the transfer function, or either Laplace or Z, right? Discrete time or continuous time. Uh, now, we always um, accepted the entire differential equation of the plant. Okay. So if it is a second order system, third order, fourth order, whatever order, right? We wrote the differential equation and then we transfer it to the Laplace domain, and we have the rational polynomial of S, which is the transfer function of the plant. Okay, just one plant, one transfer function. Okay, one differential equation. Either way, continuous time or discrete time, we have accepted the entire plant as one single differential equation. Now we are saying there's another way. You don't have to receive the plant differential equation as one equation, right? Particularly when it is a big equation, higher order differential equation, right? You can break it down into an n number of first order differential equations, right? So you have the choice. You can either handle the entire higher order differential equation, there are techniques to do that, or break down into n number of first order differential equations and deal with an n number of equations. But they're all first order, very easy to deal with. The latter approach is what is called the state space model. So we are going to learn it now. Right? So there are a lot of advantages modeling the plants in the first order equations, right? And n number of them. You can actually figure out a lot of things in the control system. If I mention few names of these topics like observability, controllability, right, and all these things, and we have to deal with linear algebra in state space model, because simultaneously you need to maintain a set of equations. So obviously we align with linear algebra, the matrices, etc. Okay, right. So with that, we can uh, get to the contents of the subject, state space. Right. So let's look at this differential equation. Right. It's a second order one, right? Second order differential equation. You have dy d square y over dt plus a2 dy over dt plus a0 yt is equal to b0 ut. So there's some sort of control input ut, and it drives yt. So you have y dot, y double dot, right? This is the dynamics of the plant. Now what we say here is that take your response y and assign it to a variable called x1t. So x1 is a variable you are bringing from outside, right? And it has x1, x2, x3, x4 like that. right? How many of these you want depending on the size of the equation. In this particular case, because it's a second order differential equations, we're going to need two of them, right? First one, x1t, we assign to this one, and x2t, we assign to this one, dyt over dt. Okay. So if this is a moving thing, you can say y is the position, dy over dt is the velocity, and d square y over dt square is the acceleration. Okay. So when you accelerate the vehicle, the velocity changes, the position changes, right? Uh, so, and y is what we want to monitor, let's say, right? Sometimes you want to monitor velocity as well, depending on the requirement. So we have two second order system, and therefore we have two state space state equation, variables. X1 is the first state variable, x2 is the second state variable. Okay, right. You do not assign a third state variable to acceleration here, right? Because this is second order differential equation. So you're going to need two state equations, two first order equations, in other words. Okay, right. Now immediately you can see some relationship between these two, right? So if you compare x1 and x2, you can say this. If you take x1t and differentiate it, right, you get x2. Of course, yes. If you differentiate y, you get dy over dt, this one. So x2 is equal to x1t dot. So you can write it over here. Now, whenever you talk about dynamics, you talk about variables changing their value. So for a variable to change its value, it needs to have a rate of change or first derivative. Now you have your first derivative of variable x1, right, which is equal to variable x2 because we have selected assigned that way. It doesn't have to be the case all the time. Okay, this particular case it happened. However, the important thing is that you have an equation for the rate of change of one of the state variables. So this is a big plus. When you have the equation for rate of change of a state variable, you know that you can track it. You can predict the value of the variable after one step, two steps, whatever. So you got to know the rate of change of all of the state variables. If you want to actually predict what's going to happen to the plant, where's the vehicle after some time, what is the velocity after some time. If you are able to, if you want to predict all these things at a future time, you're going to need the rate of change, and then you integrate it and predict the future value. So what about the second state variable, which is x2, right? This one. What is the rate of change of that one? Well, this one over here is the rate of change of x2, of course, right? And it is coming from the dynamic equation here, right? There's an equation 1. From that, you can say, okay, rate of change of x2 is equal to this term on the right-hand side, this term on the right-hand side, plus this term. This is already on the right-hand side. So this is that equation. This one, a0yt goes to the right-hand side as minus a0 x1t, because this is x1. And the other term, a2 dyt over dt, goes to the right-hand side as minus, this is 1, this is 1, okay, not 2, a1 x2. Then there's this term on the right-hand side, b0 ut. Okay, now we have two state equations. Now, state equation is an equation which has an expression for the rate of change of one state variable. So this one here the rate of change of x1, this equation over here, the state variable rate of change of state variable 2. So this is the process of initial steps of converting a differential equation into state equations. If you have a second order differential equation, two state equations, and they are both first order. You can see this is a first order equation. So is this one, right? And if you have a fifth order differential equation, you're gonna have 5 of these first order state equations, right? Clear. Now, how to manage 5 equations at once? Okay, you have to assemble all these things in a array structure, matrix structure, then you can move it. Right, so these are the two state equations. Now let's arrange it in a matrix format. So on the left hand side, we have rate of change of x1 and x2. On the right hand side, you're going to have this matrix, right? It's coming from the two equations, right? If you look at the first equation, right, it is simply x dot 1 is equal to x2. So when you multiply this matrix with this vector, you get that, right? Plus 0 times u. Yeah, there's nothing else. First equation is simply x1 dot equals x2. That is the first equation. Second equation is x2 dot is equal to minus a0 x1 minus a1 x2 plus b0 u. That's the system equation, right? Then we give it a label for this matrix A, this vector B, and this x1 and x2, the two states in one vector. We give the vector x without writing 1 or 2 or whatever is x vector. We call it state vector. In this particular case, we have two state variables. So a state vector is 2 by 1 vector. And on the left hand side, you have the rate of change of state variables, and we combine all of these rates of change of state variables and give it a label x dot, right? Now let's identify one of these state variables as our response output. Okay, so let me take y as our output. Y is basically x1 here. So therefore, out of the state vector x1, x2, we have to pick up the first one, x1, as our output y. Okay, so y is equal to 1, 0 times the state vector. When you multiply, this will be equal to x1. So x1 is y. That is what we call as the output, right? So with that, you have set of state equations, right? And you have matrix A, which is the system matrix, and you have vector B, which is the drive vector, and you have C, which is the observation matrix or output vector, right? So this is what is called the state space then I want to show you another one here, right? Coming from a different area, heat transfer, okay? It's a temperature control system, and you can see a container of oil, and inside that container, there's another container of oil, right? And there's a heating element like this. You provide some heat to the coil, and that heat goes to the oil volume here, right? Volume 1, and then that heat goes from that volume to the volume of the inner chamber, that is volume 2. So volume 2 heats up evenly, right, because of the surrounding oil. So, and there is some heat going out of the this system to the ambient, the environment, right? So that is the plant. So what we want to monitor is these temperatures, probably temperature of the inner chamber, theta 2. And what is the control signal? Of course, it is Q1, right? So can we derive the transfer function? Of course, I think you can do that. So what about the state space model of the plant? So let's see how we can do that. Now, before we do that, you need to know something about this area, thermodynamics and heat transfer, right? Every time control engineers, they dwell into various domains, right? There is domain-specific knowledge, right? The fundamental principles, theories, etc. in that domain, right? You may not know all these things, right? Outside the control systems, right? So you better work with domain experts every time you venture into various areas. So this is what we do in when we do research. Sometimes we undertake elephant research. We deal with elephants, right? A lot of human-elephant conflict-related problems, and sometimes we work in biomedical area, right? And then we deal with doctors, and we get their perspective, their comments, all these things, right? Before we design anything. And in elephant case, we talk to wildlife department, the vets and all, right? The park rangers, because it's not our strong area. And we also deal with sometimes traffic controls. Then we need to talk to traffic engineering department, civil engineering, or RDA, right? Like that. Make it a habit. Every time you venture, one of the basic things of the control systems engineers is they design things for other people, other processes, other applications. So you got to know something about that domain, right? Before you design these things. So in this particular example, there are fundamental principles, right, of heat transfer. So let's look at what these things are. You got to know two things at least, right? That is change of accumulated heat of a volume, right? Change of accumulated heat of a volume causes its temperature to change. So temperature changes because of the accumulated heat. If it loses accumulated heat, temperature drops. If it gains heat from outside, it increases the temperature. That's number one. Number two, heat flow from one volume to another is proportional to their temperature difference. That's important. Heat flow is proportional to the temperature difference. It goes from a low temperature to high temperature, right? Even within the volume, but here we don't look at that. We think volume 1 has the same temperature, which is obviously not the case, right? You know, when you think of a volume of oil and you heat it up, around the heater, you get a higher temperature, and other areas lower temperature, and gradually you transfer the heat even within or through the same volume. But don't look at that right now. We assume volume 1, volume 2. They have their specific temperatures. Heat goes from volume 1 to volume 2 based on the temperature difference. Okay? Right. So with that, you can write down heat transfer equation for volume 1. What is that? This is the rate of change of the temperature, right, of volume 1. So what is volume 1? If you look at that one, this is volume 1. It gets heat from the heating element, and it loses heat to the internal chamber. And also it loses heat to the outside world. Right? One input, two outputs. So this is the input, right? Control input. heat flow into the volume 1 through the heater, and Q0T is, or QOT is the heat that goes out to the environment, and Q2T is the heat that goes into the volume 2. Okay, and you can actually write it down in formal equations like this. M1 C1 theta 1 dot, so that is the rate of change of heat in volume 1. M1 is the mass, C1 is a specific heat capacity, how much of heat is required for 1 kilogram of mass to change the temperature. So it's like that, right? And this is the rate of change of temperature. So this is the entire thing is the heat flow rate, right? Change or rate of change of heat in that volume 1. Input is Q1, outputs are like that. So I can write whatever heat goes out to the environment is because of the temperature difference. So I can say theta 1 is high temperature, theta O is the outside temperature. Let's say it is lower than this one. So heat goes from high temperature to low temperature. And this is a proportionality constant, K1, 0. Okay, from volume 1 to 0. 0 means outside. And some heat goes into the inner chamber based on the temperature difference. So again, we assume volume 1 temperature is higher than the volume 2 temperature. So theta 1 minus theta 2, and the transfer rate is K12. So that is our first equation. Second equation is for volume 2, and rate of change of heat in that volume is M2C2 theta 2 dot, right? Which is equal to QT. Whatever heat that is that volume 1 loses, right, goes to volume 2, right, in this Q2 term. So it comes over here. So it is K12 theta 1T minus theta 2T, right? Okay. Now this is our first equation, right? We write it like that. We expand and get theta 2, theta 1, and theta O, outside temperature, right? In that format, you can now get a feeling that theta 1 is a variable, theta 2 is another variable, right? State variables, and their rates of change are there. So now things are actually becoming a bit more clear, right? And also whatever heat goes out is a separate thing. It is not a state variable. I think you can understand that also. And also there's a control signal, Q1, right? All the pieces that we had in the previous example are here as well. Right, now you can see both equations, they are now, we align them in a similar manner. This is theta 1, theta 1, theta 2, theta 2. This is plus, this is minus. Plus is when you receive it, minus is when you lose it, okay? Right. So now you can put them into a metric structure. Rate of change of theta 1 is like that, right? And you will see theta 0 heat going out, all right, from Q1, and also heat input from the heating element. For theta 2, there's no heat going out from theta 2 because theta 2 is surrounded by theta 1 or volume 1. And it doesn't get any heat from the actuator because heat comes directly to volume 1, not volume 2. So therefore, these things are zeros, right? Okay. Now we can see this is x dot, this is A, this is x state vector, this is the drive matrix here. In fact, when we say drive matrix, you might be confusing because theta 0 is just a waste of energy to the outside, so it's not driving anything. Drive vector is basically when you have Q1T. So if you want it in that format, you can break this into two units. One is for theta 1, theta 0, and the other one is for Q1. Then you can easily figure out theta 1 as the drive matrix, whatever comes in front of that drive vector, and whatever comes with in front of theta 0 outside is just a disturbance. Like disturbances are everywhere. I think you understand that if it is a air conditioning system, if I open the window, I lose some heat and hot air comes in. So that is a disturbance, right? Here also you are losing heat to the outside world, and we regard this as a disturbance. Right, now important thing is that you have the state space model now, which means you have the elements of the state space model, A, B, X, and X dot. And now you have to figure out what is my response, what I really want to monitor and control. So I think it's one of these variables, right? If you say, okay, theta 2 is what I want to monitor, then you can write down another equation. We call it output equation. Theta 2 is equal to 0, 1, theta 1. When you write down the output equation, you always write it related to the state vector, because the state vector is at the center point here. In the state space model, the center point is state vector. You relate state vector to various things, output equation here and state equation here, right? State space model. Okay, now in this example, we don't have that relationship we had between state variables in the previous example, which is precision, velocity, acceleration. They are successive differentials of position, right? Here, we don't have such a thing. State variables are individual variables in the system, theta 1 and theta 2. Right. Because why I explained two examples to you, that a lot of people think that when you assign state variables, it has to be one variable, and then the second one is the rate of change of that, and so on. No, there's no such thing. Any questions, please? Is everything clear to you? All right, then. Let's work out this example, right? So I want to give you a few minutes for this. It's a class exercise. This is the first system, any control system student, right, would undertake, would solve, right? Is the MCK system, mass spring damper system, right? You have written down differential equations, it becomes a second order, right? And you design various controllers for this one, shock absorber, everything, right? Now, can you derive the state space model for this one, right? Write down the equations, figure out the state variables and the state equations, and figure out your state space model. I'll give you a few minutes. And before that, I want to see some activities in the chat. Okay, it's clear. Okay, fine. Excellent. Right. We'll take 5 minutes, right? I think 5 minutes is enough for this simple exercise. I want everybody to get going, right? You may not be able to reach the finish line. That's fine. But I want you to take an effort, right? Write it down, sketch it, write down equations. If you can have to refer to some other materials, you can do that as well. Try to get me, first identify the state variables, right? And then state equations, then put them together in the state space model. Right. So clock starts now. So let's see the answer. Right. This is the mass spring damper system. You have the weight of the mass, and there's a force upward, right? And K is the spring constant. When you pull it up, the spring will pull you down. Okay, K times Y, and Cy dot is the damper force. When you pull it up, damper also resists that motion in this manner. So here we have not included mg, the weight of the mass, right? If you want, you can include that as well, right, over here as a disturbance. All right. So even without the mass, you can write down this equation, right? Suppose this is horizontal, right? Then you are writing the equation horizontally. So the weight of the mass is acting vertically, so you can just neglect that. But in this configuration, you have to add mass as well if you want to have very accurate model with the disturbance, that is weight. So the equation without the mass, without the weight actually, is upward force minus downward two forces, ky minus cy dot is equal to mass times y double dot, right? Y is our variable that we want to measure. So we when we arrange it in a differential equation format, highest derivative is my double dot, and then you have other derivatives, right? Cy dot and plus ky is equal to f. So you have all the dynamics on the left hand side. Dynamics means rate of change and higher derivatives of y, and on the right hand side you have the control signal forcing function. Okay. So you see, you now put state variables x1 to y and x2 to y dot. This is very similar to the first example we worked out. So your first state equation is x1 dot is equal to x2. Okay. And then the second state equation is x2 dot is equal to, of course, y double dot. But you get an expression from the system transfer function, system differential equation for that one, and keep all the things outside, just like over here. This is your second state equation, right? Y double dot, but it is x2 dot. So y double dot is a second derivative, but in our state equation, it becomes a first order equation, or x dot, in fact, x2 dot. Now, you can see that higher order derivatives are now broken down into first order differential equation, but set of them, right? Now, when you assemble the system, where on the left hand side you have x1 dot x2 dot vector, rate of change of state variables. On the right hand side you have x1 x2, that's a state vector. In front of that you have the connection matrix, right? The system matrix. And also on the right hand side 0 1 f 0 1 f. So had you considered weight also here? Weight will also come as disturbance, but not a control signal. F is a control signal. You manipulate that signal, but gravity, the weight is a disturbance. So this is your A matrix. This is your B vector. What about C? We have already assumed Y is the variable we want to monitor. In fact, Y is now x1, first state variable. You want to monitor state variable 1. Okay. So how do you get first one of this state vector, right? Of course, once you multiply 1 0 row, you get this one extracted. So it is 1 0, the C vector. Okay, right. So let me know how many of you have got it right completely. How many of you have got it right? Please raise your hands. Okay, yeah, good. Only one person. How many? Yeah, somebody said Mr. Negri. Fine, that's fine, fine. Yeah, it's important that you take few steps. Okay, how many of you have got halfway? You can raise your hands. Halfway, like you you got the different you got the system dynamics first, because that's obviously you need that, right? And then you have to assign state variables, then you have to write down state equations, then you have to develop the state space model. So there's 4 steps. Yeah, halfway means first 2 steps, say differential equation and then state equations. I get some answers. Yes. All right. Some people have done it. This exercise is very important for you to really get the grip on the state space model. Right, fine. Now we are back with this one. Right. So the next thing about state space is that is the state transition. Right. So what is state transition? Now the entire plant is now modeled by a set of state variables, x1, x2, and so on, right? So if you look at that MCK problem, right? You have position, you have velocity, you have acceleration. Okay. So acceleration, if you look at that problem, what is actually the plant here? Is it position, velocity, acceleration, or is it position, velocity, or is it just position? What do you think? Well, it depends, right? You can say, okay, if I want to control acceleration up to that level, right, then that is also a monitored variable. But I'm referring to generic cases, right, where you have a differential equation, any order, and you assign state variables and write down the state equations. You build the state space model. So in that process, if you look at the mass spring damper system, the acceleration is directly connected with the external force. So whatever force you give to the system, right, it's gonna change the acceleration first. It's directly connected to the acceleration, and as a result of that, velocity changes and then the position. Okay, so therefore, what we regard as state variables are position and velocity. The acceleration is not regarded as a state variable, right? Reason is control signal controls the acceleration in order for the state variables to change. Usually, you do not have any control signal from outside connected to state variables directly. Usually, you don't have it. Any controls you have are connected to the rate of change, connected to the rate of change of state variables. And if it's a single control signal, it goes to the rate of change of the highest state variable. So again, if you look at the position, velocity, acceleration thing, the highest state variable is velocity, and the control signal goes to the rate of change of that, and that is acceleration, which is not a state variable. Okay, right. So I think that discussion is enough on that. Now, state transition means how the state changes. See, you can see it on here, the graphics, right? You have x0. You have x0 here. That is the state at time 0. So you have position and velocity at time 0. And this is the state at time t, position and velocity at time t, right? So the state goes from time 0 to time t through a certain profile, right? This is what's called state transition. And initially, we, let's not take any control signal here, 0 controls, and you let the vehicle, if it's a vehicle or if it's a mass spectrometer system, you just let it move, right? Let it function. And after some time t, you measure what's the state. If it's a vehicle, you stop the engine and it's just coasting, right? And after some time, you measure the position velocity, right? It's like that. So this process, how do we track down this process? Right. So we start with the state space model x dot is equal to ax, right? So this is very special relationship in state space modeling. You get this equation like that. Plus the other things we do not consider right now, right? Because the title here goes like without control input. So we don't have any controls. We don't have any disturbances. This is the simplest thing to handle. Okay. Right. So system drives itself, okay, because of the stored energy. Now, we are trying to use this relationship because there's a rate of change here. We know things is going to change. And after some time, we want to measure the state. So what we do is we take Laplace. Then x dot t becomes sxs minus x0, right? A simple Laplace transform. And on the right hand side, axs. This is something you have done already. To fair distance is a repetition of what you have done, but after that, it will divert to a different direction. And then you can take this axs to the left hand side and keep all xs terms on the left hand side and other terms right hand side. So you can see the initial condition x0 on the left hand side, it goes to the right hand side. And you simplify this si minus a, this goes to the right hand side as inverse, and you have this expression. Okay. If you want to get time, because we want to calculate the state in time domain, right? So it has to be time domain. So let's come back from Laplace to time, right? X s becomes xt, and this becomes Laplace inverse. Laplace inverse x0. X0 is a constant. Now, if you look at this equation number 5, on the right hand side, you have initial condition x0. What's on the left hand side? Xt. This is exactly what we wanted to have, right? Xt, the state at some time t. Now, who calculates this transition? It is this matrix in the middle. This matrix in the middle. So therefore, let's call it state transition matrix, right? And we give it the symbol big phi t, right? So what is it? Si minus a inverse and Laplace inverse. Try to remember that. If you have the state space model and you have the matrix A, you put it into this format, Si minus A, get the inverse, and then work out the inverse Laplace. when you put that together with x0, right, you can calculate the state at time t. T is a variable which is over here, right? You can set it to any time, 5 seconds, 10 seconds, 5 days, whatever, right? You can calculate xt of all the state variables, x0, x1, x2, x3, and so on. There's no x0, x0 is this one. I mean, x1 state variable is the first state variable. Simple, right? But it's very, very powerful because you can track down all of the state variables. Now, if you compare this with the previous things that you studied, let's say in semester 1, you are tracking YT, output. Now you are tracking not only output, all the other state variables. If it's a position, velocity kind of thing, you measure all these things simultaneously. Is it clear? Or anything which is not very clear, please let me know. Is everything clear to everybody? Any questions? All right. There's some activity in the chat. All clear. Good. Now, let's be a bit more particular here, right? So, let's take this equation number 4 here, right? Rate of change of state variables on the left-hand side, state variables on the right-hand side with some matrix in the middle, right? This is a first-order differential equation, set of differential equations, right? It is the relationship. But what's the solution for this one? The solution is what is xt? What is xt, right? Of course, we have some solution here. Right? Let's keep it aside for the moment, right? Whenever you solve the differential equation, you get something like this. Xt is equal to something times you can have the initial conditions, right? So that is the solution. This is the dynamics, how the system changes. This is the value of the system after some time, right? There are two different things. System equations or system dynamics is how things change, there are relationships, rate of change, etc., etc. And the solution means what is the value of the plant at any moment of time, like this equation. Now let's assume as one solution of the system dynamics here, equation number 4, right? Let's assume e to the at x0 is a solution. Let's assume, right? In calculus we do that. We assume solutions and then put it into the dynamics and see whether it satisfies the dynamics. If satisfies, then we say, okay, fine, this is a solution. So if xt is equal to e to the at x0, this is a solution, very similar to number 5 here, right? Very similar to number 5, but it's not number 5, it's a different expression, right? We want to test whether this is a solution. Then if it is, if you want to check whether this is a solution or not, we want to bring it from here to here and check whether it satisfies dynamics. So to do that, you need to differentiate this one. Okay, that's how you get x dot. When you do that, you want to see this right-hand side shaping up to this right-hand side. Then if it is the case, fine. So this is the candidate solution. We don't know it is a solution or not. Then we differentiate it. Then left-hand side becomes x dot t, like here. What happens to the right-hand side? A is a constant, then xt. So whether we can get that one from here. So e to the at, when you differentiate, it becomes a e to the at, and this is a constant, right? The right hand side will change a e to the at x0. And of course, what is e to the at x0? This one, e to the at x0. This is equal to xt. So you replace this one with xt, and the answer is a times xt. So what you have got here is, after differentiation and substitution, is x dot t is equal to a times xt, which is equation number 4, right? So you assumed a solution and you differentiate it, and you got the system dynamics. So this is a solution. So is this one. Equation number 5 is a solution, and this one is also a solution. So the solution should be equal, because the system cannot go right this way as well as that way. We don't know such systems, right? It is going through a certain dynamics and end up over here. So therefore, if this is a solution and this is also a solution, they should be equal to each other. So the state transition matrix here is also written as e to the 80, e to the 80. Right? You can work it like this, or you can work it like that. So this is our final conclusion. Laplace inverse of Si minus A inverse, right, is also equal to e to the 80. And this is collectively termed as state transition matrix, of course, without control input. Okay, we have not considered control input. And this is what is called the famous Cayley-Hamilton theorem, right? E to the 80. This is matrix exponent, right? One way of writing it is this way: a to the k, t to the k over k factorial when k 0 to infinity, right? This is numerically implementable version of this e to the 80. And in computational platforms like MATLAB, they make use of Cayley-Hamilton. Right, for your exercises, you can stick to e to the 80 or this one, okay? So let's work out an example. I want you to take a little few steps here, like what you did in the previous cases. This is the example. Obtain the state transition matrix of the system. This. You are now given state space model, rate of change of state variables x1 dot and x2 dot, and system matrix, and this is the state vector, right? Here there's no need to write the output equation, which of these state variables are actually monitored, right? We want to get the state transition equation, right, from one state to the other state, right, in time 0 to time t. And this example is already solved. You can carefully work through it. State transition matrix is equal to Laplace inverse of S minus A whole thing inverse, right? We have seen that. One approach is, okay, try to build it. Right. This is A, and you write down Si minus A. So Si minus A means I is identity matrix, diagonal elements are zeros, other elements are zero, diagonal elements are ones, other off diagonal elements are zeros, all zeros. And Si means diagonal is S, basically, right? Minus A is this one already given, and this is Si minus A. Now you want to take the inverse of that. matrix inversion, right? When you have a matrix inversion, you write down the cofactor matrix over the determinant. There you can see diagonal elements swap each other, right? S plus 3 over here, S comes over here. And the off-diagonal elements, they change the sign. This minus becomes plus, this plus becomes minus, and divided by the determinant. Again, determinant is you multiply the diagonal elements and deduct the product on the off-diagonal. So S plus 3 times S plus 3 times S minus 2 times minus 1, minus 2. Right, so you can write this as S plus 2, S plus 1, because it's the same thing. This is S square plus 3S plus 2. You can write it as two expressions like this. So then what happens is that this S plus 2, S plus 1 thing goes into the bracket here, the matrix rather, and every element in the matrix is divided by S plus 2, S plus 1. And this is Si minus A inverse. So you have got down to that level, Si minus A, and then the inverse of that. Okay. Now what you want to do is to take the Laplace inverse of that. Laplace inverse of that, right? Can you take a minute or two and get me the Laplace inverse of that? Give it a try. All right, 3 minutes. How many of you have given a try, and how many have got the answers? Please raise your hands so that I can get a count. Okay, we get few hands going up. That's very good. All right. So let me show you for the others how it is done, assuming the one who raised the hand got the right answer, like this. So we want to get the Laplace inverse of this one. Okay. So the previous slide, you can see this one, right? You want to break it down into partial fractions, right? Because it's so easy to do that in Laplace table if you break it down to small fractions, so that you can see the similar entries in the table, right? So this is the first one, second, third, and fourth. The Laplace inverse of these are all similar types, right? Something always plus 1, something always plus 2, and that's a very basic format. And you can clearly see in Laplace inverse, it is e to the minus something, right? All of these things. So this is actually 2 times e to the minus 1t. So 1 over s plus something, when you invert it from Laplace to time, it is e to the minus that something which comes with the s in the denominator. Okay. So this is e to the minus t. This is e to the minus 2t. This is e to the minus t. This is e to the 2t. E to the t. E to the 2t. Like that. It's not difficult. It's not difficult. It's just a matter of being familiar with Laplace table a little bit. There are only few entries in the Laplace table that are coming over and over again very frequently. If you don't look away, right, to these entries, you will be fine with most of the sums that we solve in control systems, right? So bit of patience and affinity to deal with these entries in the Laplace table will pay a lot, will benefit you, right? Will help you handle most of the sums. So now you put them together, this as the state transition matrix. Remember, Now it is the state transition matrix, because you have got Si minus A and then inverted it, and then you did the inverse Laplace of that. So it is the state transition matrix. So you can write the state transition equation here. On the left hand side, it is xt. It's not x dot t, it is xt. On the right hand side, you have the state transition matrix and then the initial conditions, x0. So this is somewhat similar to the dynamics of the plant, state dynamics, like this, for example, x dot t equals axt, right? But don't get it confused. This is dynamics and this is solution or state transition equation. The dynamics and the state transition. Here, you don't have x dot t, but xt. On the right hand side, in place of a, you have e to the at or it, the state transition, and then initial conditions. Okay. Now, if you know x10, x20, initial condition of state 1, initial condition of state 2, you can actually simulate this whole thing for the given system. Now, this one is something like this, coming from a plant. You know A, right? Now you have the state transition matrix, right? This A is not visible now, but the elements of A, they have gone into these exponential expressions here, e to the 2t, 1t, etc., etc., right? So you can get the x1t at some other time from 0 to t, 5 seconds, 10 seconds, whatever. You can immediately calculate the position, right? And then you can actually see for yourself how x1 changes over time, how x2 changes over time, right? How state changes, transit from one time to another time. Is everything clear?
Yes, sir.
All right. Now let's see state transition without the control signal, right? You have certain profiles. Every state, x1, x2, x3, and so on, right? They have their profiles. But the moment you bring in the control signal, you are giving more energy to the plant, right? You are modifying these dynamics, right? So then the state transition profiles are going to change, right, to a different set of profiles. And this is most often the case because systems have the control systems more often than not, okay? So in that case, how do we do the same thing again, but this time considering the control signal also, right? Let's look at that. So we write down the equation now, x dot t is equal to axt plus but. We have brought in the control signal, okay? Right. This is now much more complete. If you want, you can bring in the disturbances as well, right? But usually we don't do that. Okay, now let's let the process continue here. The first step is take Laplace. So this is x s in front of that s, right? Because of the differentiation. Then minus the initial condition x0. On the right hand side, axs plus bus. Then you take xs to the left hand side, it becomes si minus axs. Right hand side x0 plus bus. Then you try to isolate xs over here. Si minus a goes to the right hand side as previously. It becomes si minus a inverse here and here. This is what we had earlier we have dealt with it, done, but this is a new term, right? New term, and it's a convolution integral. My God, it's coming again here, right? See, this US is a Laplace function. Si minus a is also a Laplace function, and two Laplace functions are multiplying together. When it happens, we know it is a convolution integral. Oh, yeah, there's some activity in the chat that says why we analyze it without control input in the first place if that is practically not available. Well, now systems are sometimes autoregressive, sometimes exogenous. Exogenous means, I think we have done this in the first semester. Exogenous systems, they have external signal, right? Most of the control plants and all that, they have control signals and they drive the plant, right? But on and off, sometimes it's coasting, free running. It's like when you drive a vehicle, most of the time you drive it, right? And sometimes you can see people put it in the neutral and, right, don't do anything, just let the vehicle move, right? That is coasting. And then position, velocity, acceleration even changes gradually. Acceleration becomes zero actually, and other variables change. So state transition happens without control input because of the stored energy. Any system which has some energy stored in it, right? If you don't do anything, something will happen to that energy, right? So if that energy cannot be released, it will stay like that. But if it is allowed to move and dissipate that energy, it will do that. So the system will move, right? State will change from present to something else. Okay. So when we analyze systems, we have to analyze for both cases. Both cases. When you want to control a plant, right? Now, if you look at control systems, a lot of other areas than controlling, right? System identification, then optimum parameter adjustments and all these things, right? Passive systems, of course, if you look at vehicle suspension, mostly passive. Nobody's controlling it, right? So in that, when you want to design that, you want to see how the system transit from one state to another, right? Okay. Is that clear to, I think, Vitana or somebody, right? Vitana Siri, yeah. Vitana Siri, is that clear to you?
Yes.
Okay. So now we have this second term coming up. Now we know that's a convolution integral. All right. So let's deal with it. The first one, we don't want to do anything. We have done it. It is phi t x0. This is state transition without the control signal. Now see how beautiful it is. You have two things separately. You can work out this one and this one separately. Any change in the system because of its own dynamics, it's over here, autonomous part of that. And this is exogenous part. State variables change due to external inputs, right? So we are talking about linear systems. Because of that, you can separate these things out and work it out. But if the system is not linear, you can't do any of these things. That case is a bit difficult. Okay, all right. Probably we'll have time towards the end to deal with nonlinear systems like say inverted pendulum or quadrotor plants. They're all nonlinear, right? There are sines, cosines, square terms, etc. How to deal with those systems? We'll have little time for that, maybe towards the end of the semester. Right. So we write this one, right, as a convolution integral, right? That is integration from 0 to t If you look at this one, right, Si minus A inverse, right, you can see the same thing over here, right? Same thing over here. So Laplace inverse of this one, right? Laplace inverse of this one is actually the state transition matrix, phi d, right? So here also you get the same thing, state transition, right? Once you do the Laplace inverse, like here. But this time, that matrix, state transition matrix, and this ut, which is the control signal, right? They are convoluted. So therefore, we write it like that. Phi t minus tau b u tau d tau. Okay. Any questions about that? The convolution integral. Okay. Now, if we first take the transition from T0 to TT from equation number 9, I think that's this one, right? You get equation number 9, state transition, even 10, right? Oops. Sorry about that. Right. So you can write down this equation. Let's say equation number 10 directly, right? From that, you can write this equation xt0, right? xt0. See, t0 is a timestamp, right? You're coming from x0, 0 time, right? So if you follow this equation, right, t becomes t0, and this is 0 anyway. This state transition is from 0 to t0, 0 to t0. And if you look at the example, right, example we worked out, this t is actually the duration from start to end. Okay. So there you can see it, 0 to t, 0 to t, right? It can be from any time to any time. But you need to look at the difference, time difference, and that is what goes in here. Otherwise, it would be a little bit confusing. This t is not just the final time, it is the duration. If you start with 0, then you can just simply say t, of course. But if you start from somewhere else, not 0, this is not correct. Okay. So therefore, when you write down the phi, then the sub t, right? This t subscript is very important. It's not the absolute time, right? It's a time difference. So to account for that, what we do is we write down from 0 to some time t0 as, say, intermediate time, right? And this becomes phi t0, right? And this is 0 to t0. This convolution integral is up to time t0. And this is t0 minus tau b u tau d tau. Oops. I want to take this little further, and therefore I don't think I would be able to finish it up today. But let me try. Let me try. We don't want to drag it too long. Yeah, just additional few minutes, right? So then you can write this down as once you have this one, you can get an expression for x0. So get x0. This is the initial condition, right? which is equal to phi t0, which goes to the left hand side, and you get the inversion of that, okay? And then you have on the left hand side xt0 anyway, and this whole thing goes to the left hand side with minus t0, sorry, 0 to t0, this whole thing. That is equation 11, right? I think you're following it. So this is an expression for the initial conditions at time 0, because we are going to get rid of this time 0 thing. Otherwise, you might believe that you have to start with time 0, x0 all the time. No, it's not the case. Then what we do is we substitute this one on equation number 10. Equation number 10. Right. So once you do that, equation number 10 has this one, xt. Initially, we took, I think, 9, right? Oh, well, the only difference between 9 and 10 is that you have the convolution integral. So it's the same thing. So we put it back on number 10, right? In place of x0 and see what's going to happen. So then number 10 says xt is equal to phi t, right? And x0. In place of x0, you have this big expression, you bring it over here up to this point, plus the other term, right? 0 to t, phi t minus tau, bu tau d tau. Okay? The only thing you did is bring in this expression for x0, initial condition. Now, you can multiply these two together. This is phi t, this is phi t tau, this is inverse. Now, when you see inverse, if it is an exponential term, inverse means you change the sign of the exponent, right? So therefore, this t0 becomes minus t0, right? If you look at state transition matrix, we show that it is equal to e to the at. Remember that? You can write either phi t or e to the at. Now, they're same. Now, if you look at this e to the at thing, right? If you have this inverse of that, it becomes e to the minus at, right? So this is in fact e to the minus at0, whereas this one is e to the at. So when you multiply them together, it becomes e to the a t minus t0. There you can see t minus t0 is the gap of time, right? If you move from t0 to t, you don't have to move from 0 to other times. You can move from any time t0 to any other time t. So we want to get that expression. That's why we are following this process. And then this is xt0, not x0. It is xt0, right? Any other time t0. So it comes over here. Now see, this is shaping up very, very similar to equation number 10, where we started off with time 0. Now we start off with time t0 to t. And then time difference is t minus t0. So it comes up over here. And when you write down phi, it is not just t0 or t, it is t to t0 or t0 to t rather. So what happens on the other side? So you have this expression and whole thing comes over here like that. And then this integration plus this third term over here. So what is this? This is phi t minus t0, right? And this is 0 to t. So 0 to t is positive, and t0 to t is negative. Is negative, right? So everything else remains the same. Now, if you see phi t0 minus tau, bu tau d tau, this is 0 to t0. This is 0 to t. Okay. So this is negative, this is positive. So you can see the substitution. Eventually, it will be t0 to t. T0 to t. Okay. Right. Now, if you look at equation number 12, it says this. You can start off with any time t0. Not necessarily 0, time 0, right? Any state at time t0. And you can use this equation, right? You have the transition from that time to another time t, right? You can see the time difference. This is the homogeneous part, and this is state transition times control signal, right? You get the convolution integral from t0 to t. That's it, right? On this graphics, you can see time axis 0, t0, t, right? There's a transition from 0 to t0, and there's another transition from t0 to t, right? And you can have a third transition from 0 to t. All these transitions are handled by the same equation. Only difference is that you set your initial time, final time. That's it. Any questions, please? So I will, if you can take a snapshot of this one, as you see, right? You can work out this one at home, right? This is an example. Obtain the state transition equation of the system for unit step input. There you are. There is an input unit step right over here, right? And you have state transition equation. And this is very similar to previous example, the same plant. Why don't you give it a try, right? Work it at home, right? Next week we'll look at that. Any questions, please?
Sir?
Yeah.
So this is Ashfaq Ahmed MSc 19 batch. So once you end the session, can I have a?
I replied to the in the chat. Yeah, you may remain. Yes, we can discuss that. Okay. Yeah. Any questions from the students? Is everything clear? Yeah, I will upload the lectures. Yes. Right. Right. Everything is clear. Okay, fine. Then let's wind up the session. And Ashfaq, you can stay. And I'll see you next week. Bye-bye. Have a good evening.
Thank you, sir. Have a good evening.
Thank you.